Okay, so now we are going to calculate the empirical formula from experimental data, or as our book calls it, calculating the empirical formula from combining masses. So this means we use mass data instead of mass percent to calculate the formula of a compound. So here's an example. There's a reaction where we take 2.14 grams of copper and react it with oxygen, and it nets 2.41 grams of pure substance. So the assumption here is that the 2.14 grams of copper is in the product now. But there's also something else in the product. What is that? Well, it's oxygen. So this is kind of interesting. It's almost like burning copper, and then the mass of the copper product becomes larger, which is the opposite of what happens when you burn wood. You burn wood, and the mass becomes smaller. Well, it turns out in this particular case, the oxygen bonds to the copper, and since the copper is a solid along with the oxygen, the mass increases. Whereas with wood, when the oxygen combines with the carbon in the wood, it becomes CO2 and it escapes as a gas. The oxygen also combines with hydrogen as H2O, and because you're burning the wood, the H2O is very hot, it's steam, and it kind of fades away. And so what are you left with? You're simply left with the metal compounds combined with oxygen, or metal oxides in your product. The metal oxides, of course, weigh far less than the metals plus the carbon and the hydrogen in the wood. So that's why it seems like the wood is losing mass. It really isn't. The mass is going up in gas. Okay, so here what we're going to do is instead of taking the percentages and turning that into moles, we're going to find the grams of each element. So if there's 2.14 grams of copper in the product, then the amount of oxygen must be the difference between the mass of the product and the mass of the beginning copper. So we have 0.27 grams of oxygen. We then take these two masses and determine the moles of each element. So here the molar mass of copper is 63.55 grams per 1 mole. So we use the molar mass kind of upside down, as it were, and we get the moles of copper. We use the molar mass of oxygen, and we get the moles of oxygen. Now you might say to yourself, well, but wait a minute, that's 0.27 grams of O2 that reacted. Okay, fine. 0.27 grams of O2 times 1 mole of O2 per 32.00 grams of O2 times 2 mole of oxygen per 1 mole of O2. And the reason we do that is because we don't want moles of O2, we really want moles of the element atom, okay? So when we do all this multiplication, can you see that 2 divided by 32, put 16 on the bottom here? Just like that, you get the same answer. So that's why I assume that we just put 0.27 grams of oxygen in there, single atoms of oxygen, when really it was O2 that reacted. Okay, so here we use the moles as subscripts. Which of these two numbers is smaller, 0.03 or 0.01? Well, 0.01. So I divide each of them by 0.0169 and I get copper 1.995 and oxygen 1. And that ends up being copper to oxygen. So here I don't need to make any sort of adjustments because I have nice whole numbers. And the empirical formula of this compound is Cu2O, whose name is copper 1 oxide. Now, why is this called copper 1 oxide? And the answer is because the charge on each copper ion in this is +1. Copper 1 oxide. Okay, so here's an example of doing a formula of a compound from combining masses. So oxides of virtually every element are known. Bromine, for example, forms several oxides when treated with ozone. Suppose you allow 1.250 grams of bromine, Br2, to react with ozone and obtain 1.876 grams of BrXOY, what is the formula of the compound? Remember, the goal is, 1, take the grams of Br2 and turn that into moles of Br, and also take the grams of O2 and turn that into moles of O. So let's start off with that. 1.250 grams of Br2 times 1 mole of Br2. You'll notice I'm not spending a whole lot of time showing you how to calculate molar mass because, number one, we've done that a number of times. And number two, it's review for you from your previous chemistry class. So for bromine, we get 79.90 times 2. 79.90 times 2, which should be close to 160. 159.8 grams of Br2 times 2 mole of bromine per 1 mole of Br2. So roughly, I'm going to have 2.5 over 159, which is going to be a pretty small number, much smaller than 1. So let's figure this out. 1.25 times 2 divided by 159.8. And we get 0.015644 or 45 mole of Br. Now, how many grams of oxygen are there? Well, we take our 1.876 grams, subtract 1.250 grams of bromine, and that's the grams of oxygen, times 1 mole of O2 per 32.00 grams of O2. Each oxygen is 16, so 2 of them is 32, times 2 mole of oxygen per 1 mole of O2. And let's see what we get here. So 1.876 minus 1.250 should put us at what, 0.63 or something? 0.626 times, or I put divided by, so I'm going to go back and put times 2 and then divided by 32. So we get 0.039125 mole of oxygen. And this is good for, the difference here is good for 3 significant figures. So this is good to there. So we get Br 0.01564.5, oxygen 0.039125, and we're going to divide by 0.015 for each of these. So we get bromine 1, oxygen 2.5008. And this is going to be good to right there. So that means we get bromine, oxygen 2.50, which becomes Br2O5, because you can't have a fraction as the number of atoms that you have. So that is the empirical formula of the compound. So first, you get the moles of each, then you take the moles of each and figure out the formula. Now, let's take a look at hydrates. So this is still kind of figuring out the formula of a compound. So hydrates are ionic compounds with water in the solid. These are solid materials. So this is an example of a hydrate. This is called cobalt 2 chloride monohydrate. It's cobalt 2 because each chlorine is actually a chloride ion with a -1 charge, so the cobalt has to be a +2 charge to make that neutral. One H2O is called monohydrate. Now I don't call that water because this is a solid. So this does not behave like water. It behaves like a solid piece of H2O, but not at freezing temperatures. So cobalt 2 chloride monohydrate. There's another hydrate with cobalt 2 chloride where there's two of the hydrates. So what do we call that? Cobalt 2 chloride dihydrate. And there's yet another cobalt compound with 6 hydrates. So cobalt 6 chloride hexahydrate. Now, we're not going to memorize the names of any hydrates per se, but if you're given the formula of something, you should certainly be able to figure out the name of the hydrate. There's monohydrate, dihydrate, trihydrate, tetrahydrate, pentahydrate, hexahydrate, all the way up to decahydrate. So those prefixes are the same as you would have that we've seen previously. The one where I said September is like hepta, October, octa, November, nona, December, deca. Okay. So let's look at how we would determine the formula of the hydrate. So this is a lot like determining the formula of a compound. So to do this, we want to determine the mass or mass percent H2O in the compound. Okay. So to do this, we determine the mass of the dehydrate or the mass percent dehydrate. Use the mass percent H2O and the mass percent dehydrate to get the moles. Moles, I should say, mole ratio. And then here's how you get the mole ratio. Now, as far as this explanation goes, we'll come back to this. Let's take a look at using this in a problem, okay? Then we'll come back to this. So, determine the formula of a hydrated compound or a hydrate. You want to know the value of X in blue hydrated copper 2 sulfate. So there it is. So is this copper 2 sulfate monohydrate, copper 2 sulfate dihydrate, copper 2 sulfate trihydrate? What is it? So here you weigh out 1.023 grams of the solid. So that's the hydrate. After heating the solid thoroughly in a porcelain crucible, you have 0.64 grams of nearly white anhydrous. An means without, hydrous, water, without water, or I should say hydrate, copper 2 sulfate. So we have 0.64 grams of copper 2 sulfate. We can take that amount here and we can figure out how many moles of copper 2 sulfate. So the tact here is to figure out moles of copper 2 sulfate and then figure out the moles of H2O, and then we'll call that, let's call this A, and we'll call this B. And then what we want to do is we want to take B divided by A to get X, the value of X. So what do we get for the moles of copper 2 sulfate? We have 0.654 grams of copper 2 sulfate times 1 mole of copper 2 sulfate, and per how many grams? Let's see, what did I do with my calculator? I had it here just a moment ago. Oh, it's right here. Okay, so to figure out the molar mass of copper 2 sulfate, I need to know that copper is 63.55 grams. I need to know that sulfur is 32.07 grams. And I need to know that 4 oxygens is 64 grams. So I have 159.62 grams of copper 2 sulfate. Now, why am I calling this copper 2 sulfate when there's no 2 in the formula? The answer is because that's a copper +2 ion, copper 2 sulfate. Okay, so we take our 0.654 divided by the 159.62, and we get 0.004097 mole of copper 2 sulfate. So that's 1. 2, how do we get the moles of H2O? Well, first we need the mass of H2O. If we started off with 1.023 grams of the stuff and it had H2O in there, and it ended up being 0.654 after all the H2O has been removed, then I think the amount of H2O is the difference. So we have 1.023 grams minus 0.654 grams of H2O. And then we're going to multiply by 1 mole of H2O per 18.0, let's see, 18.0182828 grams of H2O. Okay, so 1.023 minus 0.654. That should give us around 0.35, right? So I get 0.369 divided by 18.028. So we get 0.020468 mole of H2O. And then what we do is we take that number, 0.020468 mole of H2O, for every 0.004097 mole of copper 2 sulfate. So I need to divide this by 0.004097. And you can see that this is basically, if you look at it this way and kind of cover this up, it's 4 into 20, so I should get 5. And I get 4.9959 mole of H2O to 1 mole of copper 2 sulfate, which means we're going to get copper 2 sulfate dot 5 H2O. And this is called copper 2 sulfate pentahydrate. And that's how you get the formula of your hydrate. Now, I'll be honest with you, when you do these experiments, it's rare that you get such beautiful numbers. So in the real world, you might get something like 4.8 mole of H2O. And what you have to decide is, well, how good am I? Am I good enough to get 4.99, or is 4.8 as close as I might get on my first try when I'm new at doing this? Well, you might very well figure that 4.8 is correct and it's going to be 5. But, you know, the way you would find out if it really were rounded to 5 is you would try to repeat this experiment until you dial it in. Okay. Next, we're going to look at something called instrumental analysis, determining compound formulas using an instrument, okay? And the instrument in question here is something called a mass spectrometer. And a mass spectrometer gives you something called a mass spectrum. So we want to identify molecules really using mass spectrometry. Now you see the word isotope in here because isotopes play a role. So this is a about mass spectrometry. And this is a cartoon of a mass spectrometer. So this is the meter. The technique is called mass spectrometry. All right. So here you can see the device looks like a bent tube because it is a bent tube. And here at this end of the tube, you have the detector. And at this end of the tube, you have the sample introduction into the instrument. So when you introduce the sample into the instrument, you want the sample to be a gas. There are many different ways of turning things into a gas. One of them is simply heating it. Another one is something called laser desorption, but there's all sorts of different ways of introducing your sample. But mass spectrometry works pretty much the same for regardless of what the sample is. The sample could be an atom. The sample could be a compound. It can be a really big compound. You can do mass spectrometry on DNA, on proteins, really huge things. And here's how it works. Once you turn the sample into a gas, because it's a gas, the molecules are moving in all sorts of directions. And some of those molecules are going to bounce through this little hole here. Now, this hole here is in the middle of this thing called a repeller. The repeller has a positive charge. Now, when the gas particle passes past this electron gun, the electron gun has enough energy to knock an electron off of the molecule. So if you knock an electron off the molecule or atom becomes positively charged, and we call that a cation. So this trap here is to make sure that electron doesn't go bouncing around all over the place. Okay, so imagine that you have a positively charged particle here now because an electron has been taken off of it. That positively charged particle will be repelled by the repeller, and hence the name repeller. It will be attracted by the accelerator, and hence the accelerator. Your book may show you that you have more than one accelerator plate. Regardless, this positively charged cation will be attracted to the accelerator. A lot of these ions hit the accelerator and become neutralized, game over. But some of them go so fast that they pop right through this opening, and they are basically slingshotted or shot forward. Now this is a magnet around the tube, and the reason the magnet is there is that it's tunable so that you can change the flight path of the cation. So you can tune the magnet to where it changes the flight path very little or a whole lot. Now, the flight path gets changed depending on the mass to charge ratio. Okay, so if it's a very massive particle, it's going to want to go straight with its momentum and not be changed very much. So you got to turn that magnet up a lot to turn a huge particle a lot. A small particle, the magnet can turn the flight path very easily. And so here, this might be a small particle with the magnet. And here, this solid line shows a mass to charge ratio that's just right, the Goldilocks mass ratio. Now, what is the Goldilocks mass ratio? Well, it depends on the magnet. And the magnet you can adjust so that any particular mass to charge ratio is the Goldilocks one. So when we talk about mass to charge ratio, we're talking about AMUs to charge plus 1. So we always try to make this a plus 1 charge. And so we go through all the different mass to charge ratios one by one. So what's the smallest mass to charge ratio? Well, you could have a mass of 1 AMU and a charge of 1. 1 divided by 1 is 1. You could have a mass of 2 divided by 1. So mass to charge ratio of 2. So the mass to charge ratio will be 1, 2, 3, 4, 5, so forth and so on. And the reason these are pretty much whole numbers is because you have to remember that we're looking at relative masses, and the relative mass of a proton is 1, neutron is 1, electron is 0. So the masses of all these things coming through here are going to be built out of isotopes, which have whole number masses. Okay, so we can tune that detector, tune the magnet so that the right charge to mass ratio or different charge to mass ratios reach this. So what you do is you set it for like 10 seconds for a 1, 10 seconds for a 2, 10 seconds for a 3. I'm actually exaggerating. You set it for like a 100th or a 1,000th of a second for 1, a 1,000th of a second for 2. But the deal is that you make the time frame for each different mass to hit the detector the same amount. So therefore, in that time frame, if you get nothing hitting it, then you say, well, I've got none of that mass to charge. In that same time frame, if you get 2 hitting it, you've got 2. If you get 4 hitting it, you've got 4. So that means there's 4, if you look at the 4 versus the 2, the 4 has twice as many proportional isotopes as the 2. So you go through all of these mass to charge ratios, and it takes you like less than a second to do 1,000 different mass to charge ratios. This is a fantastic instrument. Costs about $100 to buy one of these. So we happen to have a couple of these in our lab, but they're always hard to keep up. We've never had the training to fix them or to operate them. And they were gifts from crime labs in Eureka. Okay, so let's take a look here. And let's look at isotopic abundance by mass spectrometry. So we have that the mass spectrum of phosphorus trichloride is illustrated here. Now, phosphorus trichloride is PCl3. So the fact that there's no prefix on phosphorus means there's only 1. The fact that we have tri in front of chloride means there's 3 chlorines. Now it says that phosphorus has 1 stable isotope. So when we look at phosphorus, there's only P31. Now, how much does P31 weigh? And the answer is 31 AMU. Now, chlorine has 2 stable isotopes. Chlorine 35, which weighs 35 AMU, and chlorine 37, which weighs 37 AMU. Okay. All right. Now, it turns out that when we look at the ratios of 35 to 37, roughly it's about 75% 35 and about 25% 37. Okay, roughly. All right. Now, here's the mass spectrometry. Here's the mass to charge ratio. And what we're supposed to do is we're supposed to take a look at what all of these are. What do they indicate? So these are called the parent ions. The parent ions are the group of ions that are the largest. So let's take a look at this 136, 138, and 140, and this little tiny blip at 141. What might those be? Well, if you have a phosphorus and 3 chlorines, you could have a phosphorus 31, a chlorine 35, a chlorine 35, and a chlorine 35. So this is one molecule. You knock an electron off, it hits the detector. What is the mass that this thing has? Well, let's find out. 35 times 3 is 105, plus 31 is equal to 136. So I'm going to put U there. So if you have phosphorus trichloride with this one phosphorus and these exact isotopes of chlorine, it weighs 136. So that's what that is. So what do you propose for this peak here at 138 that weighs 2 more than this? Well, I think it's going to be 31 phosphorus, chlorine 35, and one of them is going to be chlorine 37, because that weighs 2 more than that. That would be 138U. So you can probably figure out what this peak is at 140. How many chlorine 37s are going to be there? 2. How about this 140? Well, you have all chlorine 37s. And you might ask yourself the question, well, why is the 140 so tiny and the 136 so large, where the 140 has 3 chlorine 37s, the 136 has 3 chlorine 35s? Well, the 136 ends up being bigger because there are more chlorine 35s than there are chlorine 37s. So, can you figure out what this guy is, this 101? Well, what about a 31 phosphorus plus a 35 chlorine plus a 35 chlorine? Now, what I should really be doing here is I should be putting a plus charge on these, because they're all cations. So what's 35 and 35? 70 plus 31 is 101. So what do you think the 103 is? Okay, so here, I'm going to let you figure out the 103, the 105, and then predict the structural formula of phosphorus trichloride from the mass spectrum. So if we take a look at this guy's probably going to be phosphorus 31 and chlorine 35, because what, 31 and 36 is 66, right? So the question here kind of begs, what's the structure look like, the structural formula? Well, it looks like you can pick off individual chlorines, right? So does that mean that you can have a chlorine at the center of all of it? Probably not. So here, this might be the structure, because you can imagine one chlorine peeling off at a time. And one of these atoms has to be in the center. So that's isotopic abundance by mass spectrometry and how you might do this. We're going to be looking at a lab, a dry lab about mass spectrometry pretty shortly. All right, and guess what? That's the end of this section. All right, thank you for listening.